starting again, and I'll talk about another somewhat different deployment of OpenStack in a system called Chameleon. And Chameleon is a platform for computer science research. So it's very interesting listening to the previous talk, because actually we share some problems in common. One of them is that the infrastructure as a service platform need to evolve rapidly, right, to meet the needs of advancing science. But we also don't share some problems in common. So having working with the computer science community means that people are less choosy as to the interfaces of the system and much more choosy as to the knobs that they can turn, right? So we are working with folks who, I should just do general introduction to Chameleon. See that slides are rendering a little bit differently. So it's a computer science testbed, a system that has been in existence almost 10 years. We celebrated our 9th birthday recently, at cake, virtual cake, but still. And over that time, we had the privilege to serve over 11,000 users working on computer science research and education. That community collectively published over 700 different research papers in computer science. And those are papers on things like new operating system design or energy efficiency or performance variability on different architectures. So those are research projects that require deep reconfiguration, the ability to stand up things on bare metal nodes, boot from custom kernel, and so on and so forth. So the system has been in existence for, or the project has been in existence for over 10 years. So you get a picture of one of the first nodes that we ever got, and then segging into the first Raspberry Pi rack that we ever deployed, as eventually we had to move to support edge hardware. So moving forward, Chameleon is Chameleon in a nutshell, a few things that are important to know about the system. So the first thing is, of course, what I already said. Chameleons like to change. We emphasize bare metal reconfigurability in order to cater to all the computer science research projects that we support. But since inception, we always supported a small KVM cloud as well, because we also support education projects, and not everybody needs bare metal for research. And if you don't, then it's more efficient to use the system through a virtualized offering. And lastly, we moved to support experiments at the edge with Raspberry Pis, with NVIDIA Nanos, with IoT hardware. So you see this little self-driving car, more about that later. This is one of those cars with NVIDIA on them that are able to run inference while driving. And this is a type of experiment that we now support on Chameleon, but we don't support it via bare metal reconfiguration. We deploy containers on those cars or Raspberry Pis in general, as they're much more lightweight. And then second thing is we try to support as much diversity in the system as possible. Because again, those are computer science experiments. Everybody is chasing the latest architecture. So we've got, we're trying to have every new architecture that comes up. We've got, of course, Intel nodes, AMD nodes. We also have Fugaku nodes. Fugaku, the second fastest supercomputer in the world. Configured based on ARMs, just in interesting configurations. And we have, all sorts of generations of GPUs, very diverse set of different SSDs for storage researchers to experiment on. And we also do have disaggregated hardware. So we've got both Liquid and GigaIO, if anybody here is interested in experimenting with those new architectures. So it's a distributed system. It used to be that we had two sites, one at the Texas Advanced Computing Center, one at University of Chicago, which we're using the ALCF, the Advanced Leadership Computing Facility at Argonne as the machine room. So we used to have two supercomputing centers as Chameleon sites. In we just recently got renewed for another 4 years of the project. So in this new iteration of the project, we invited NCAR to join us as a third Chameleon site. So now we've got 3 supercomputing sites in a nice triangle, which allows you to experiment with different networking topologies, so more interesting distributed experiments, and that also allows our user community to use 3 different sites. So very important to us because our user community is growing very fast. So it's still growing, not only large, but still growing. But we also support volunteer sites. So we've got a system called Box, which is packaging of Chameleon, and we support volunteer sites. So NCAR, in fact, joined Chameleon several years ago as a volunteer site, and they were volunteering so well that we invited them to become a core Chameleon site. But we also have volunteers in other places at Northwestern, at UIC, and now a system called National Research Platform also created a Chameleon site. And we sometimes have hardware legacy programs where we give away hardware that from our perspective is old, so like 4 or 5 years old. So this is still very serviceable hardware, but not the cutting edge architecture that our users expect, but still very useful for educational projects perhaps. And that allows others to create Chameleon sites. This was a very popular program. The world needs more OpenStack sites, right? So talk to me if that sounds interesting. And then, of course, we're based on OpenStack. I generally say it's about 50% OpenStack, 50% special sauce, which includes things like access via federated identity, network stitching, and things like that, and more about that later. And lastly, we promote using the platform as reproducibility, and I'll circle back to that later as well. So one thing important to know about the system is that it's not just an OpenStack deployment, not just a system, but also a community of users, very tightly knit community of users. And you've got a collage of pictures taken at various different times of our users, presenting at conferences, working in their labs, receiving awards, participating in competitions, and so on and so forth. And all of that is, you can find their stories in our blog. So every month we profile one of our user experiments. It's very inspirational to others because if it turns out that somebody can run experiments with self-driving cars, so can you, right? So you read about how they did it, and then you do it yourself. And now switching to the edge a little bit. So several years ago, we realized that more and more of our users were interested in edge computing. They were running experiments with federated learning, network traffic, fingerprinting, all sorts of IoT devices, but we did not provide those experimental capabilities. So the only way they could use Chameleon for those experiments is really via some sort of simulation or emulation. And for an experimental test bed, that's not a good look, right? That's not a good look if your users can only do something via simulation. So we started looking into providing edge capabilities and went through multiple iterations of what this looked like. And we had sort of a bit of a debate because most of our users would say, we just want exactly what Chameleon is right now, just for edge, right? So we want to look at a lot like a cloud, and we want to be able to structure experiments from edge to cloud from one Jupyter notebook. But then, of course, it's not a cloud. It's edge devices that are out there in the deployed in the field, deployed by somebody else than us, right? Somebody other than us. Typically, they are connected to some IoT peripherals, to cameras, or some peripherals that measure temperature or barometric pressure, or do things. And I'll give some examples later. But the location is very important. It's very important that it's not in the data center, and that breaks a host of assumptions. That breaks a lot of assumptions, right? So you're dealing with a host network that you can't control, for example. You're dealing with a lot of factors that you can't control. And also, of course, those devices are not server class. They don't support IPMI and all of the other things that we came to rely on. So broadly speaking, we settled on something that does reconfiguration via container deployment, supports a framework for, well, supports IoT peripherals, but mostly framework for adding support for your IoT peripherals, of which there seems to be an infinite number of various things, and people are inventing new ones every day. And very importantly, support something called bring your own device, which allows our users to add their device to the test bed, right? So not just something that we have in the data center, but something that they can deploy in the field. And they rely on us for structuring secure sharing of those devices between them and their collaborators, and discovery and all the creature comforts that you have when somebody is operating infrastructure for, maybe not all the creature comforts, but most of them. So we developed something like this several years ago. In the summer of 2021, we had many groups experimenting with this edge extension of Chameleon. We put all the results of that. We had a workshop afterwards, put all the results of that into a workshop report that you can peruse if you're interested. So here I wanted to give you an example of what you can do with this sort of edge to cloud installation. And that's a Flutter project, which is also our project. It's unrelated to Chameleon, but it's using a modification of Chi at Edge to emphasize usability, because it's not working with just computer scientists, it's working with people who want to measure broadband. So what this project does is it deploys 1,000 Raspberry Pis nationwide to measure broadband, right? So it runs broadband tests. Broadband, to really understand it, you need to measure it in people's homes or businesses, or the points where it's consumed. So we're deploying it both for the purpose of computer science research. So for example, to understand what happens to broadband in conditions of oversubscription, or if you're dealing with aging hardware, which, by the way, I included a helpful picture of what kind of aging hardware exactly we're talking about. It was amazing to me to understand what happens in some places. So both computer science questions, but also social questions, trying to understand and ultimately bridge the digital divide in our society. So we're deploying devices, for example, in a South Shore neighborhood of Chicago, which is an underprivileged neighborhood, and in Logan Square, which is a very solidly middle-class neighborhood, and comparing what kind of service those different neighborhoods get. The schematic that you see there is from San Rafael in California, which again is underprivileged neighborhood. We've got, if you go to our website, there is an interactive map where you can see where those devices are currently deployed. So far we deployed on the 500 of the 1,000 of devices. The project has been in existence for just a couple of years. But the idea is that we can run various broadband tests on those devices, but others can too. So there are many different ways in which people want to measure broadband. So the urban broadband, different type of measurement than rural broadband. Some people just measure broadband for telehealth. So it's a specific set of, it's not about whether it's good or bad, it's about whether it serves my application, right? So we're working with multiple groups who are deploying their applications on that deployment of Raspberry Pis. And in the last 7 months or so that the deployment actually happened, we were able to run, we produced a data set of 11 million data points, and spans 17 different providers, so you can compare across providers. It spans different technologies, so you can compare across that, and so on, so forth. If you're interested, it's publicly available on the website. But how powerful is this data set, right? So that it's not about how much data you have, it's about what you can do with that data, and is it going to change the world? So since we've been only at it for 2 years, we've had 2 major successes. One is a deployment in Marion County, actually demonstrated that about 1/3 of the household was below federally mandated levels. And deployment on Beaver Island, which was also a small deployment, challenged the FCC broadband maps and led to reassessment of broadband coverage for the entire island, right? So we've had some impact, we were able to do things, very real things. So moving forward, since I have only 5 minutes left, we're also moving to measuring rural wireless, which is a slightly different problem than measuring broadband. And we're adding more control into the system. So I said it had to be simplified in order to be deployed easily, had to be deployable like an iPhone kind of thing. You open it and it works. Now we're complicating a little bit. We're adding GPS to improve the accuracy of the measurements, as well as to be able to, for example, to find the location. Put the devices on campus buses, drive around the campus and measure broadband there, or drive around areas, measure broadband there. So I'll just fast forward through a bunch of other applications. This is a project with NCAR of 3D printed weather stations. They're actually using microcontrollers that we're connecting to through the Raspberry Pis, using the Raspberry Pis to, in addition to monitoring weather, also look at pictures of clouds and things like that. Sensor stations for marine and coastal ecosystems that measure qualities, have multiple sensors on them, can be added to buoys that they already deployed, and then can do processing on the buoys. AutoLearn, I already mentioned that this was something that we developed in collaboration with one of our users from Rutgers. He was teaching machine learning to kids, essentially by teaching them how to operate, or how to train and then operate self-driving vehicles. And we said, well, can we adapt it to Chameleon and to very commodity mainstream vehicles that you can get from Amazon? And a couple of years ago, we had some students working on that project who developed a module that others can now use to do self-driving experiments on Chameleon. And there are many, many other projects that predict air quality with federated learning. We're working with a group in Purdue on soundscaping. This is when they deploy microphones in a forest, turn them on every so often to listen to the sounds in the forest, and then can reason based on that what animals are present and what noises the plants make, and things like that. Precision agriculture, so that's instrumenting greenhouses to look at plants, meteorologic monitoring, and others. And I won't talk about them later. One very exciting thing that I wanted to say is that supporting computer science is one thing, but how do we now support others to experience this computer science research experimentally, not just by reading papers, which is what I would do today, right? I would go to ACM Digital Library and look for research and download papers on that, but by reproducing somebody else's experiments, right? So can we have a hub of experiments, so like ACM Digital Library, but just experiments, not papers, right? And if we had that, I could go to that hub and I could look for experiments that interest me, but also I could look for the methodology that those experiments were created with, right? So what was the experimental environment they used? Maybe I could also look for what was the data analysis that those people used. Maybe that was the point of their result. It happens in computer science very often. So we're trying to promote this. We call it practical reproducibility. It's a great application of test beds and experimental infrastructures to provide shared resource on which people can replay each other's experiments. And if you're headed to supercomputing, we have a workshop on the first day, on the Monday of supercomputing, where we're hoping to get all the authors and reviewers of papers. So Chameleon supported the reproducibility initiative at supercomputing, also supported reproducibility initiatives at many other HPC conferences. So we're trying to get all those folks together and listen to their experiences and understand what else needs to happen to infrastructure to support those experiments and support reproducing those experiments really well. So if you're interested, please come and talk to us. For some reason, the Earl is not here, but if you go to chameleoncloud.org, that should be right on the website there as one of the first announcements. If you don't see it, look at announcements. Okay, so parting thoughts. First of all, edge to cloud, right? So we stretched OpenStack a little bit, not just in the data center. Now, you can submit through OpenStack interfaces elsewhere, right? So in order to do that, it was like mostly special sauce with some OpenStack garnish on top. But what our users see as OpenStack interfaces, which is important. Secondly, we're not just talking about data center anymore. We're definitely going out of data center. And for that, we're going to need networks and we're going to need distributed infrastructures. So we're partnering with a project called Fabric. In the US, it's an NSF-supported core network reconfigurable infrastructure. So you get control over your network pathways. A lot of experiments need that. Power, PAWR, is our NSF wireless test beds. Again, if you're deploying in the wild and wireless is your main way of reaching those devices, you may need to control that. And National Research Platform. And then I wanted to also say there are different facets of Continuum. When people talk about edge to cloud continuum, they usually emphasize the distribution aspect. But there's more to it than that, right? So when you're talking data center, we're building an HPC data center in particular, you're thinking, well, power plant, right? You need significant energy to power this, all the way down to maybe a solar battery that you include with your edge device, right? And somewhere in between there, you're just plugging things into a socket. There's configuration continuum, bare metal to containers. Operational expertise, your users become part operators of those devices, and so on and so forth. We're invested, well, it's now really time to talk about bare metal versus virtualization face-off. We're going to have in Chameleon phase 4, but one last plea, come and join us for the workshop. If you're interested in reproducibility, we'd love to see you there.
Great, thank you. I think I did see the URL for your workshop, reproduciblehpc.org.
Yes.
Yes, it was on the slide. Okay, it was on the slide. So reproduciblehpc.org. Any questions for Kate before we break today to head upstairs? Yes. It's always the people in the back. We appreciate you being here, I promise, even if you're in the back.
So this is less one of those less a question, more a statement questions. But if you're interested in how we built this, come talk to me, find me at the break. I think there's some really interesting stuff about shared ownership of worker nodes and methods for sort of distributing control plane and data plane traffic. And there's a lot of cool stuff here. Especially given the recent talks about like Binder Hub and how do different users run experiments. I think there's a lot to talk about. So come find either of us.
I should say Mike is the infrastructure lead for Chameleon. So while I focused in the talk on the use case and usage patterns that we see emerging, Mike is the person, probably the best person to ask about how all this special sauce and this garnish, how that all hangs together.
I love that you refer to it as special sauce. Kate and Michael, thank you so much.